Hello everyone, welcome back to the HasMotion YouTube channel. Today I will be presenting the 7th Visual 3D tutorial, which will overview model-based calculations in the application. This can be described as the calculations that only make sense relative to rigid segments, or more generally, body segments like the thigh or torso which behave as rigid bodies during motion. A general rule for this is that the distance between any two points within the segment remains constant, regardless of how the segment moves. This tutorial was written to be accessible to a broad customer base. However, the interfaces and techniques described are exactly the same approaches used for the most sophisticated analyses. Part of the power of Visual 3D is the ability to determine exactly what and how calculations are done, and the ability to point to the published works proving its validity. From a pure tool perspective, the power is in additional pipeline command parameters and options. Just like the last tutorial, it may be helpful to review the command pipeline video tutorial and documentation on the HasMotion wiki page. In this tutorial, we will examine the analysis characteristics of the positions of the pelvis and foot during gait, knee flexion and extension, and knee joint moments and powers. To do this, we will define segment angles, joint moments, and joint powers. We will also be reporting on basic attributes such as stride length and other fundamental gait characteristics. The overall process of the analysis will go as follows. First, we will create a report with basic gait information. Next, we will calculate joint angles to measure left and right knee flexion / extension. And third, add the computed signals to a report. First, make sure to have downloaded the tutorial3.cmz file from the tutorial wiki page. I have this loaded into the Visual 3D application workspace already as seen. You can load this in as well by selecting the open file icon on the toolbar here. Once loaded in, we can navigate to the Signal and Event Processing tab to visualize an animation of the model based on the movement data and the model that was applied to it. So we can click on Signal and Events here, and it will move us to the tab. If the animation doesn't appear in the 3D animation viewer, as we can't see it here, we have to check the combo box on the top right and make sure it says Walking Trial 1.c3d rather than all files. Now that this has been loaded in, we can see that the model has appeared. Our first step in this tutorial is to compute joint angles. Joint angles are defined as the orientation of one segment relative to another. Because we are dealing with 3D space, there are a series of rotational transformations involved in the calculation. A joint angle is not the same as a 3-point or 4-point angle in which there are projections but no transformations. Visual 3D lets you pick any two segments in which to measure a joint angle. They do not have to be connected or even be near each other. In practice, joint angles are calculated as the transformation from one segment A to another segment B using the local coordinate system of segment B as the frame of reference. It is essential that you select the proper Cardan sequence based on a complete understanding of what you're trying to measure. In Visual 3D, you can select the Cardan sequence that you want, which relates to your specific data. The default Cardan sequence used by Visual 3D is the ordered sequence of rotations X, Y, Z, which assumes the following. X being flexion and extension, Y being abduction / adduction, and Z being longitudinal rotation. One of the options for joint angles is to select normalization. This is not generally recommended, however. Normalization means that when the segments in the movement trial are in the same relative posture as the same segments in the standing trial, the joint angle is considered 0. The problem with the calculation of a normalized angle is that the standing posture and the movement trial should both be aligned with the laboratory axis. Getting a patient to stand oriented relative to the lab may not be possible in some situations. An alternative approach is to create virtual segments which define the desired angles in the standing posture. An example of this is available on the documentation wiki page under the title Normalized Joint Angle Method 2. Now we can start on creating a joint angle for the right knee. In the application, from the Model drop-down menu in the main menu bar, here, we can select Compute Model-Based Data. This will prompt the following dialog box to appear. The information needed to be entered will be displayed in the image. In the data name box, we can create a joint angle called right knee angle. The link model-based property is a joint angle, so we can select joint angle in the model-based item property drop-down box, like this. As we can see, the default normalization is off, and then the segment will be the right shank, so we can select it from the drop-down, right shank, and the reference segment will be the right thigh. This will also be at the drop-down, and we can select right thigh. The cardan sequence XYZ is automatically selected for us, and this is the equivalent of the joint coordinate system. Now we can press the create button. The joint angle is created and a processing dialog shows if any errors were encountered. This dialog also contains which files were processed, which is important to note because signals are only created for active files. Now we can press OK and close. Now in the same dialog box, we will be creating the joint angle for the left knee. We can enter the information seen in the image displayed. This will be the corresponding left side parameters to the previously created right knee angle. In the data name box, we can fill it out as left knee angle. And in the model-based item properties box, we can select joint angle from the drop down. We can leave the normalization as off, and then the segment will be left shank, and then the reference segment will be left thigh. The cardan sequence can stay as XYZ, and then we can select create, and the program will run through the processing dialog. After completing these steps, we can close these tabs, these dialog boxes, and then we can look at the data tree. If we open the link model based folder, which was newly created, and then if we open the original subfolder, we can see that our left and right knee angles are present in here. Next, we can use the application to understand this knee angle signal that we have created. To do this, we can graph the X component of the right knee angle and left knee angle signals. So first, right-click the left knee angle signal within the link model-based folder and select Graph X and New Graph. So we can navigate to the left knee angle signal here, right-click it, select Graph X, and then New Graph. This will add the X component of the left knee angle signal to this area in the Signals and Events Processing tab. Then we can go ahead and do the same for the right knee angle. So we right-click, select Graph X, and New Graph. In this segment coordinate system, the Z direction is upwards and the Y represents the anterior. Rotation about the X-axis represents flexion and extension. Visual 3D always computes all signals based on the right-hand rule. This is shown in the image displayed. For example, if you point your thumb in the direction of the X-axis of the hip, pointing laterally to the right, knee extension will be 0 when the thigh segment coordinate system and the shank segment coordinate system are aligned. Knee flexion will be seen as a negative angle. Note that the X-axis for both the left and right thigh segment coordinate systems points laterally to the right. In the figure shown, the thumb is pointing in the direction of the X-axis and the fingers are curled in the direction of shank extension relative to the thigh. So knee extension is a positive angle. Using the same schema, adduction of the knee is positive rotation about the y-axis for the right leg and negative rotation about the y-axis for the left leg. Inward axial rotation of the shank is a positive rotation about the z-axis for the right leg and a negative rotation about the z-axis for the left leg. This reflection of the data anatomically from right to left is a result of applying the right-hand rule rigidly within Visual 3D. When presenting data, it is quite common for users to negate the y and z terms for the left knee angle. If we open the Compute Model-Based dialog box again from the Model drop-down menu here, and then we can select the left knee angle that we have previously created, we can now negate the y and z signals by selecting the checkbox next to them. After pressing Create and then OK, we can close this dialog. The resulting knee rotations about the z-axis, inward/outward, are positive in the same direction. We can then navigate back to the Visual 3D application to create the net joint moment for the right knee. So we can navigate to the model drop-down menu and then once again select compute model base data in order to open the same dialog box. We can reference the image which contains one definition of the right knee moment. So in this case, the data name box can be filled out as r knee underscore moment. In the model based item properties drop-down, we can select joint underscore moment this time, and then we can also check the use negative checkbox for the Y and Z signals. For the normalization, we can set it to normalize using default normalization, which divides joint moment by the subject mass. A note is that any metric value can be used for normalization. As you can see, there are 4 options for normalizing the joint moment model based signal. There's normalization off, normalization using the default normalization, normalization to local file metric value, and normalize to global metric value. So of course we can select the default normalization, and then the joint will be r knee, and then the resolution coordinate system is usually the segment proximal to the joint. So in this case, the right knee moment is resolved in the segment coordinate system by the right thigh. So we can select right thigh. And then we can click create. In this tutorial, you gained an overview and hopefully a better understanding of model-based computations in Visual 3D. If you would like to review more information on interpreting the joint moment signal or computations based on process signals, refer to the tutorial wiki page. Thank you for watching.